Right, you guys, let's jump into our next section. Here we go. We'll talk about 310, linear approximations and differentials. Very different application of derivatives from related rates. Let's check it out. Linear approximations and differentials. So two different ideas, but obviously they are closely connected. We'll start with linear approximations. What's this all about? We'll begin with an example. Without the use of a calculator, approximate the square root of 4.37. Okay, why are we going to do this? Obviously, we have calculators that are super accurate. Why do we want to do this without the use of a calculator? Okay, so a couple of reasons. So one big reason is part of learning calculus, or really any sort of major branch, is to go back and walk through the same steps as our predecessors did, right? Obviously, calculators haven't been around all that long. How did people do those sort of approximations before we had all this technology to do it for us? So we'll investigate that here, right? If we know that the steps that others have walked, then that will open it up. We can take further steps, right, and innovate for our present day. Also, just as important, these sort of techniques in calculus, I mean, these were revolutionary ways to do these sort of approximations, what we're about to see. They made finding these sort of approximations really, really fast compared to what people had to do before calculus. And it turns out even the technology that we use and how it's programmed uses calculus theory and techniques within the programming of our computers and our calculators. So just learning how it's done with calculus actually gives us insight into just how our technology even works in the first place. Okay, let's go for it. How are we going to begin to approximate the square root of 4.37, and how is it connected to derivatives and tangent lines? Let me begin just with a graph of square root of x. So I've kind of crudely drawn a square root function. Took me several attempts to get even something like that. So I hope you like it. All right, so we've got f of x equals the square root of x. And here's what we're going to do. We're going to identify a point that's kind of close to the value that we want. So I'm going to take x equals 4, because that's kind of close to 4.37. And the advantage of 4 is I can easily find its y value on the curve. All right, the square root of 4, the y value there is 2. Okay. Why should we pick a point like this? We're going to create the tangent line through that point, like so. All right, so there'll be some tangent line that passes through our point at 4, 2. All right, how is this tangent line going to help us approximate the square root of 4.37? Check it out. This is obviously not to scale, but just for the visuals, it's necessary to put 4.37 quite a distance away, just the nature of how close these curves are. So let's say 4.37 is way out here. The point on the green line is the actual value of the square root of 4.37. But it turns out that's really difficult to do by hand. What we're going to do without a calculator, we're going to find the y value on the tangent line. If we can find the equation of the tangent line, it will actually be really simple, even without a calculator, to plug that number into the equation of the tangent line instead, since it's the equation of a line and it's not curving. Let me go one step further, just really to highlight that last point. The point on the green line is 4.37 comma the square root of 4.37. That y value is the actual value. But we're not going to find that. Instead, we're going to find the y value that occurs on the tangent line. Now, in the end, we're going to know that the value that we get is not the correct value of square root 4.37. That's not the point. We're trying to approximate it, and it turns out it will be approximated really, really closely. It'd be really, really good. They look like there's some distance apart right in my drawing, but actually it should be really close in here. And those are super, super close together. And we'll see exactly how close we get. Okay. So we've kind of mapped out our game plan, how we gonna actually go about this. Once again, first step, there's two steps. First step, let's find the equation of the tangent line at this nearby point at 4,2. We'll find the equation of that red line. Once we have the equation of the tangent line, all we got to do is plug in x equals 4.37. It'll tell us the y value on the tangent line. That'll be our approximation. Okay, let's go for it. Again, there's our strategy. We're going to take f of x to equal square root x. Right? Let's think of that as x to the 1/2 power. In order to get the equation of the tangent line at 4,2, first thing we need, of course, is a derivative. So there's our f prime of x, and right 1/2 x to the negative 1/2. I recommend you rewrite that as 1/2 square root x, because we now need to plug in the x coordinate of our point at 4. We find f prime of 4, plugging in 1/2 square root of 4 gives us 1/4. And of course, that is the slope of the tangent line. We're going to go even further. We know the slope of the tangent line. We know what point it goes through. And so we can find the equation of the tangent line with our point slope form. Y minus 2 equals 1/4 times the quantity x minus 4. Now, normally we simplify those point slope forms into a y equals mx plus b form. This time we're not. All we're going to do to both sides is add that 2. We're going to leave the rest of it as 1/4 times x minus 4. There's a reason for that. So we're going to leave this like unsimplified, if you will. We'll come back to this later to make sense of why we're not simplifying. So let's just call it the equation of the tangent line, y equals 2 plus 1/4 times x minus 4. Okay, great. We found the equation of the tangent line there. Second step, let's plug in x equals 4.37. So here we go, y equals 2 plus 1/4 times 4.37 minus 4. And from here, we're going to find the y value. That'll be our approximation. Okay, at this point, so at the beginning, we said like do this without a calculator, right? So the idea was we weren't going to just find, like type into a calculator square root 4.37, enter. At this point, let's go ahead and grab our calculators just to finish this off. Now, hopefully you agree, like we could do this by hand, right? If we subtract there, it'll be 0.37. We can multiply that by 1/4. And if we thought of that as like 0.25, we can multiply those decimals. We could figure this out if we really had to without a calculator. At this point, there's no need to avoid using a calculator. Let's just grab one and crunch those numbers. And we should get y equals 2.0925. There it is. That turns out that is a really, really good approximation for the square root of 4.37. Because we live in the modern day, right? And not when calculus first came about, the 1600s, we can check this against our technology just to see how accurate we were. So we got an approximation. Now we know we're not correct, but just how close are we, right? 2.0925. You grab your calculator and you type in the square root of 4.37, right? What does a calculator give? Just how close were we? If you do that, here's what my calculator said. I put in as many digits as it produced, and obviously there's more, but mine gave 2.090454496. Now just compare those and be amazed how close we were, right? The 2.09, all that was accurate. The actual value has a 0 next. We had a 2. So what? That's 2 tenths, hundredths, thousandths, 2 1,000ths. And even what comes next is a 4 5, and we had a 5. I mean, that's really cool. So it's essentially like 2 thousandths, or if you went one further, right, 10 thousandths, like 25 or so 10 thousandths. That's crazy accurate, right? If you were building something and maybe, you know, you were measuring in meters or feet or inches or centimeters, right? If you were off by 25 10 thousandths of a meter, so what? Like whatever you're making, that's going to be accurate enough. Your tools won't even be precise enough for that to even make a difference. You know, so, okay, really, really accurate. Let's go just a little bit further, kind of tie it all in together. Let's define the linearization of f of x at a. The linearization of f of x at a is given by this formula, L of x equals f of a plus f prime of a times x minus a. Notice the way that that's written. We've got a y value here, f of a, plus a derivative value times the quantity x minus a. That whole thing, we're giving it a new name. We're calling it the linearization of f of x at a, and denoting it as capital L of x. All that is the equation of the tangent line at the point A, f of a. Right, we've got the slope of the line, f prime, and this has been added from the other side, just like we added that 2 when we were doing this a minute ago. Okay, if you don't believe me, if you're like having trouble seeing that, like, I'm gonna kind of make the connection here on this screen with the example we just did. Notice there are 2 different variables, if you will. There's x and there's a. X is the value that we're trying to approximate, where a, I like to call it an easy value to calculate that's close to or near x. Okay, let me bring back our last example, kind of show you what each of the pieces would have been. So we were trying to find an approximation for the square root of 4.37. Okay. So we took f of x to be the square root of x. Right. Notice we have an f function and an f prime. Right. So that we got to identify from what we're trying to approximate. Our x value is what we're trying to get the value for in the function. So we're going to take x to be the 4.37. A is an easy value that's near to x. So we said, hey, 4.37, and we're using a square root. You know what? The easy value near this x would be 4. I can easily take the square root of 4, and that's pretty close to x. And then our L of x, we didn't call it that in the last example, but it was the equation of the tangent line. The 2, well, hey, that's f of 4, right? F of a, plug a into your function. Plus 1/4, that was the derivative value of our function at 4, turned out to be 1/4. And then finally, times the quantity x minus 4, just putting the a in right there. And so if then we wanted to find the approximation for the square root of 4.37, we would just take our x, plug it in, we'd find L of 4.37. letting us then plug 4.37 in right there for X and do that calculation. And we would have our approximation. Okay, just one last comment. Why do we call it the linearization of f of x at a? Because it's like we're linearizing the function. We're kind of like flattening it out as if it was a straight line. Let me go back to the first screen. So when we had the square root of x, right, it's got this curve to it. What we did with this tangent line, it's like we linearized the green curve just for values that are close to the point the tangent line passes through. So you have to think like, you know what, for a little while there, that green curve almost looks like a straight line. Like we all know it's curving, but it's curving just a little bit when it's close to this point. So when we create that red line, it's like we're straightening out the function in order to make these approximations. Now, obviously, by the time we get out to this point in the drawing, they're starting to, you know, they're starting to get some distance between them, but of course, that was just for the visuals. There you go. I guess, you know what, one last thing. Notice that the point we were trying to approximate was a little bit higher than where the tangent line is. And what happened in our answer compared to the actual value, our approximation did in fact turn out to be just a little bit bigger than the actual value. Makes sense the way that the graph works, that our approximation would just be a tiny bit bigger than the actual value. Okay, that's it for this video, I promise. Let's stop here and we'll pick it up in the next one.